Put every fact in one vector store, and you will mix shared knowledge with private user state. This decision framework separates RAG evidence from agent memory. This gives you the pattern for a system that places shared facts and user facts in separate homes for fresher, deletable context. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. People build RAG and agent memory because models need relevant context, and that context has different lifetimes and owners. Product documentation is long-lived and safe to share. User preferences are private, and they change. Mix those two, and deletion gets hard. Plus, you risk leaking stale or private data into prompts. The right outcome is a system that fetches the correct product fact while applying only the current allowed user preferences. At a basic level, RAG is about retrieving shared facts from a knowledge base. Agent memory is per user state you can update or remove. The split buys you clearer control, simpler GDPR-style deletion, and fresher personalization. The cost is extra bookkeeping and a policy decision up front. Which lane does each fact belong to? We'll build a tiny pipeline that assigns facts to either RAG or memory, filters memory by recency, compares candidates, deletes a user, and then composes the final prompt. That keeps orchestration explicit and auditable, so you don't accidentally put private bits where they can't be removed. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. Let's start by separating facts so ownership is explicit. This snippet separates toy facts into RAG-owned and memory-owned context. Product facts and user preferences have different owners, so putting both into one vector store makes privacy and deletion blurry. The facts tuples make ownership visible. Product-owned, shared information becomes RAG, while user-owned, private information becomes memory. Nothing is embedded yet, because the first move is deciding where a fact is allowed to live before retrieval or orchestration begins. The output shows separate counts, proving the context split is explicit before any system reads it. Now that facts have owners, we need to keep memory fresh and forget old preferences. This example filters memory by how recently each user fact was observed. A preference that was true months ago can quietly become wrong, even if the product knowledge is still valid. Scene records when each memory fact was captured, and fresh memory keeps only facts inside the 45-day window. Increasing that window preserves more personalization, but it also raises the chance of stale user context. Decreasing it is safer, but may forget useful preferences sooner. The output shows how many user facts survive and how old the oldest checked fact is. With fresh candidates, we must decide whether shared docs or memory better answer a query. This code compares RAG and memory candidates instead of merging them blindly. The user's query is about preference, so the strongest match should come from fresh memory, not the shared product docs. Score uses word overlap as a small teaching retrieval signal, and rank applies it consistently to both stores. In a production RAG system, the same decision shape can sit after embeddings, keyword search, or a re-ranker. The output shows which source won, and the score that made that selection visible. We also need the ability to remove a user's private state cleanly without touching shared docs. This snippet deletes user-specific state while leaving shared knowledge alone. Mixed stores make deletion hard because product documentation and personal preferences can share the same index, metadata shape, and retention path. memStore keeps a user field beside each memory fact, so removing U1 is a targeted operation rather than a search across every product document. The RAG list is untouched, which is the point of separating ownership before storage. The output shows the number of deleted user facts and the memory records that remain. Finally, we combine the surviving shared facts and the allowed user bits into a prompt that respects ownership and recency. This example assembles the final context using the ownership rules already built. The policy object keeps shared RAG docs and user memory in separate lanes, so build context can combine them deliberately at orchestration time. It always chooses a shared product fact with score, then adds only matching user bits that still exist after deletion. Because U1 was deleted in the previous step, no private preference is added back into the prompt. The output shows a small, complete baseline context that respects freshness, scope, and deletion. Take this tiny pipeline and map it to a real help desk. Put product manuals in RAG and tickets and user profile tweaks in MemStore. Use scene timestamps to expire trial flags after 45 days. Use a consistent retrieval policy so support agents and automated assistants never see deleted user bits. 3 crisp points. It separates shared facts from per user state, so you can delete or refresh user data without touching global docs. Use this when personalization matters, and you need auditable deletion or freshness guarantees. One caveat is extra complexity. You must design and enforce ownership rules early, or the system drifts back to mixed stores. A practical next step is to swap the simple word overlap score for embedding cosine similarity, and tune the similarity threshold that decides which source wins, so you get smoother matches between user phrasing and product docs while keeping private bits isolated. If practical AI engineering helps, subscribe and watch for more systems and Python walkthroughs.